Hello, my name is Diego Garcia, we are team number 4 and I'm going to present the topic of rational functions.
Hello, my name is Manuel Avitia and I'm going to explain the topic of vertical and horizontal asymptote.
Hello, my name is Roberto Macias and I'm going to explain the absolute functions.
Hello, my name is Sebastián Sanchez and I'm going to explain slants.
Hello, my name is Alejandro and I will be explaining a problem concerning rational functions.
A rational function is a division of polynomial functions in which the denominator has a degree of 1 or more. We can identify simple a rational function by seeing if the denominator has a variable with an exponent. The form of a rational function is p multiplying x over q multiplying x. Here is the form of a simple rational function that is 1 over x. To know how to graph a rational function, we need to evaluate any value of x in the function. So it's f of minus 2, it's equal to 1 over minus 2. So the first value is this, and you need to do the same with the next values. So 1 over minus 1 is minus 1. Any division over 0 does not exist, so this value in the function does not exist. And 1 over 1 is 1.
Well, now we're going to explain you the vertical and horizontal asymptote. It's really easy. The only thing you need to do for obtaining the vertical asymptote is equal the denominator to 0. X minus 1 equals to 0. Then we isolate. X equals to 1. Well, in here, as you can see, it's the same value, obviously. Then for obtaining the horizontal asymptote, the only thing we need to do, and it's really easy, is just take a look at this number, okay? So, here's the horizontal asymptote, 1, and the vertical asymptote, 1.
An absolute value function can be best described as a function that contains an algebraic expression within the absolute value symbols. In further detail, the absolute value in its own is the distance of a number from 0 on a number line. For example, if we have minus 2 with the absolute symbols, the answer would be 2. Okay, so the basic characteristics of the general absolute function are the following. At least when there's no shifting, the range is from 0 included to infinity. The domain is all the real numbers, as you can see here. While the vertex, the x-intercept and the y-intercept are all 0, 0. This is the vertex and this is the x-intercept and y-intercept.
Now we're going to take a look at the slants. First, we need an equation where the higher term has a higher degree than the lower term. This meaning 2 and the lower one with 1. So, this is an improper equation. How do we graph it? First, we need to do synthetic division, putting the lower term outside and the higher term inside. And we start doing the division. After that, we're going to get x plus 2. Now, how do we start graphing it? X plus 2 is our new y-intercept from the asymptote. So, we get here plus 2 our point, and then with a slope of 1 over 1, we graph quickly our asymptote. Then, we graph, well, here x minus 3, you equal to 0, and you isolate the x, so it's x equal to 3. Then it's your vertical asymptote, and then you just graph the function.
Okay, so now to solve the problem, which is this one. First of all, we need to get our vertical asymptotes. We would have to factorize the denominator, which would give us this, y equals to x squared times x plus 1 over x plus 2 times x minus 2. That would tell us that our vertical asymptotes are 2 and minus 2. Due to the rule of the coefficients, or the degree of the leading term, we know that the horizontal asymptote does not exist, so we need to get an oblique asymptote. We would do a long division, the result would be x plus 1, and this would be how it looks. Then we graph the ordinary form of the cubic function, and we do the ordinary form of the slants.
Now, we're going to show you the previous rational function with the use of a software. As you can see, when we factorize the rational function, we get as factors of the denominator x plus 2 times x minus 2. As a consequence, when we isolate, we get the vertical asymptotes, being x equals to minus 2 and x equals to 2. Following the rules to get the horizontal asymptotes, we can observe that the numerator is bigger than the denominator in its degree, so the horizontal asymptote does not exist. Now, my partner Manuel is going to explain the process of the synthetic division.
For this line, we just did the synthetic division in which we got the equation of y equals to x plus 1. For the x intersection and y intersection, we isolated, in which we got as x intersection x1 equals to 0, 0 and x2 equals to minus 1, 0. And for the y intersection was y equals to 0, 0. For the domain and range, we also did a process that got us as a result the domain that was x is part of all the real numbers except minus 2, 2. This is because of the vertical asymptotes. Later, we did the factorization of the rational function, and we saw that the factors couldn't be cancelled, so we concluded that this rational function does not have empty holes. Well, as a conclusion, we're going to explain you the uses of rational functions in daily life. It is really important for our studies, a company, or a work, almost in every field. When we did the theoretical part of this project, we wrote an interesting problem about rational functions. It was about a light bulb company. The light bulb company used rational functions in which they needed to have different factors. For example, the cost of the light bulb, the income it wants to get, as well as the amount of light bulbs it needs for having a positive income. So using rational functions, we could use the number in which the light bulbs must be sold for having a positive income and the company having a great advance.